Hello, welcome back to Algebra 2. This is Unit 4, Lesson 5. This unit has been all about matrix theory, and we're really getting into some heavy duty stuff today. This stuff is super neat. We're going to be learning about augmented matrices and elementary row operations. So, the system of equations x plus y equals 6 and 3x minus 2y equals 3 can be written as an equivalent matrix equation. We saw that in Lesson 4. That matrix would be 1, 1, 3, negative 2 times the matrix xy equals 6, 3. We usually call this matrix here the coefficient matrix, and this one over here the constant matrix. So what we're going to be learning about today is something called an augmented matrix. So an augmented matrix is where you take the coefficient matrix and the constant matrix and you basically join them together. In other words, augment to put the to build up. So we're going to use elementary row operations to solve this system using an augmented matrix. So I do want to point out that this system of equations here, 1, 1, 3, negative 2, we're augmenting. So we're taking this and we're just going to put it right there. And what I'm looking to do, my goal is to get the left 4 elements, right? The 1, 1, 3, negative 2 to become 1, 0, 0, 1. That's what I'm looking to do. And I need to build up what I always call the triangle of power. So the first step to solving any augmented matrices is to start here at this corner, okay? Imagine this and make zeros all through here, okay? This is just a 2 by 2 matrix, so really the only zero I'm talking about is where this 3 is. That's my goal. Get a 0 there. And it's going to be a lot easier as long as there's a 1 at the top. So we'll try and stick with problems like that, but or at least problems where we can make it look like that. All right, so here's how we're going to do the elementary row operations. We're going to state what we're doing, and then we're going to do it, okay? And that's just a good way to show your work, but it's a better way. It's more important that it keeps you from making mistakes. I'm going to take row 1. I'm going to multiply it by a negative 3. I'm going to add it to row 2, and I'm going to store the result of that addition into row 2. So notice that row 1 is not changing. 1, 1, 6. Now I'm supposed to take this number, multiply it by negative 3, and add it. And we'll do it one at a time. So that would be negative 3 plus 3, and I'm supposed to store it in row 2. So that's my new row 2 value is 0. Then I do negative 3 plus a negative 2 is a negative 5. Then a negative 18 plus 3 is a negative 15. All right, we got our triangle of power because we have this diagonal from here. Everything to the left is a 0. I know it's only one of them, but that's it. So what I'm going to do now is I'm going to get a 1 where this negative 5 is. So I will be taking row 2, and I will be dividing it by negative 5, and I will be storing the result in row 2. So I'm not doing anything to row 1. That row 1 is staying the same. Row 2, I'm taking row 2, dividing it by negative 5, and putting it back in row 2. So that's 0 divided by negative 5 is 0. Negative 5 divided by negative 5 is 1. Negative 15 divided by negative 5 is 3. Okay, now that I've got a 1 here, I'm going to use that 1 to get rid of the 1 up here. And so I'll simply take row 2 times a negative 1 plus row 1, and I'll store it back in row 1. Let me just scoot down just a little bit if I can. All right, so we're supposed to multiply row 2 by a negative and add it to row 1 and put the result in row 1. 0 times a negative 1 is 0, plus 1 is still 1. Negative 1 plus 1 is 0, so that becomes a 0. Negative 3 plus 6 is a positive 3. And did we store anything in the bottom row? No. We're just going to leave that exactly the same. All right, so what does this tell me? Well, it tells me that 1x plus 0y is 3. Because we can unaugment this equation. We can take this equation right back to where it was. And what it means is that there's a single x plus a 0y is 3, and a 0x plus 1y is 3. In other words, it's telling me that x equals 3 and y equals 3. So that must be the solution to this equation. And it certainly is. 3, this was an x and y. 3 plus 3 is 6. 3 times 3 is 9. Minus 2 times 3 is minus 6 is also 3. So it works. All right. We're going to solve this 3 by 3 system using an augmented matrix with elementary row operations. So let's make our matrix. 2, 1, 1. Then 1, 1, negative 1. 2, 3, 1. We're going to augment it with the constants. So I'll just put them right here. 4, 3, and negative 4. Some people like to put a little dotted line here to keep them separate, but I don't really like to do that. I just like it to look like a big stack of numbers. All right, cool. So remember, we're trying to get that triangle of power. So that's starting here. If you draw this diagonal line, that's what I want. I want this to become zeros. But I need to do this in a clever way. I need to get zeros over here in this row first. Then I'll get a 0 in this corner. I don't want to try and get 0 and then 0 because when I do that, when I try and make this 0, I end up messing up the 0 I got before. And you don't want to mess up any zeros. Once you get a 0, it wants to stay a 0, right? So we will focus on getting the 0 either where the 2 is or this 1. That doesn't matter, but we want zeros in the 1s and the 2s. Then we'll get a 0 and the 3. All right. Well, actually, the thing about this problem, though, is that I don't like having a 2 in this upper left-hand corner if I can avoid it. Sometimes you can just divide through by something to make it happen. I can't do that here. So I'm actually going to swap. So I'm just going to, I just say swap row 2, row 1. Okay, so that's all I'm going to do. So row 1 is going to become 1, 1, negative 1, 3. Row 2 will become 2, 1, 1, 4. And we left row 3 alone, right? So 2, 3, 1, negative 4. All right, so now that I've got that, I'm going to multiply row 1 times a negative 2. I'm going to add it to row 2, and I'm going to store it in row 2. So let's do that. So I'm not going to change row 1 at all. So let's leave row 1 alone. 1, 1, negative 1, and 3. So this times a negative 2 plus this plus 2 is 0. We're storing a result back in row 2, right? This times a negative 2 plus this. So negative 2 plus 1 is a negative 1. Positive 2 plus 1 is 3. Negative 6 plus 4 is a negative 2. All right, now I could write out a whole nother step here, right? I could go to the next step to do something, but I don't have to. Why don't I just go ahead and multiply negative 2 times row 1 and add it to row 3 and store it in row 3 at the same time? I can work on 2 different rows. There's no problem with that. So I'm going to multiply this by negative 2 now and add it to that. So negative 2 plus 2 is 0. Negative 2 plus 3 is 1. 2 plus 1 is 3. Negative 6 plus a negative 4 is a negative 10. All right, we got 2 zeros. And you're typically going to be able to get those 2 zeros at the same time. All right. Next, we need to get a 0 in this bottom right-hand row. And it looks like we're really set up very easily to do that. I'm just going to take row 2, Got to use row 2. Can't use row 1 here, right? If I try and use row 1 to get a 0, I'm going to end up somehow adding that 1 back over here. All right, I can't do that. I got to use that row 2 because it's the only one that's got 0 stacked here, right? So row 2, if I add that to row 3 and store it in row 3. So just keep that in mind. Once you get those 2 zeros here, don't make them something not a 0. So as you try and work on this next row, you're going to have to use the 2 lines that have matching zeros so these zeros don't change. All right, let me just scroll down just a little bit here. All right, so what do I have now? I didn't change the first equation. Let's leave it alone. Didn't change the second equation. Let's leave it alone. We're going to add these and store them in row 3. 0 plus 0 is 0. Negative 1 plus 1 is 0. 3 plus 3 is 6. Negative 2 plus a negative 10 is a negative 12. All right, so I don't have to, but I'm going to go ahead and move to get this as a 1. We can't, that kind of moves us from what we call row echelon form to reduced row echelon form, which we'll talk more about in, I think, just a few minutes. So I'm going to get a 1 where the 6 is, so I'm simply going to divide row 3. I'm going to divide it by 6 and store it in row 3. So 1, 1, negative 1, 3. 0, negative 1, 3, negative 2, 0, 0, 1, negative 2. All right. Now that I've got that, I'm going to try and get a 0 right here where this 3 is next. I could also... No, I don't want to do that. Hold on. Let me think for a second. All right. So first off, I want to point out that we have got the triangle of power, right? We got the triangle of power. I didn't even really need to divide by 6. At this moment, I am basically done. Okay, I can tell you that. I can tell you right now that z is equal to a negative 2, and since this is telling me that negative y plus 3z, which is negative 2, is equal to negative 2 as well, I can say that negative y is equal to 4. So y is equal to negative 4. And then I also know that x plus y minus z equals 3. So I can also go x minus 4 plus 2 equals 3. So we know that, let's see here, x minus 2 equals 3, so x equals 5. Once you get those 3 triangles, y'all, you are done. You can go further if you want to try and get all the 1s and 0s, but it's really more of style points, okay? But it is a set pattern, so it's easy to program a computer to do it. So it's just up to you. Once you get those 3 zeros, if you want to keep going, fine. If you want to just do that, fine. It's not completely necessary, but for practice, let's go ahead and keep going. What I want to do, though, is I want to get rid of this. I want to get a 0 right here, okay? So I'm going to go ahead and do that by... no. That's not true at all. I want to get a 0 right here where the 3 is. That's what I want. So I'm going to multiply this bottom row by a negative 3. So row 3 by a negative 3. I'm going to add it to row 2, and I'll store it in row 2. So this becomes, I'm going to leave the first one alone. 1, 1, negative 1, 3. All right, negative 3 times 0 plus 0 is 0. We're storing in row 2. You can go ahead and write down row 3 if you want, because we are not changing it. Negative 3 times 0 is 0, plus a negative 1 is a negative 1. Negative 3 times 1, negative 3 plus 3 is 0. Then that makes that 6 minus 2 is 4. All right, now that I'm at this point where I got 0, 1, 0, I can go ahead and just divide row 2 by a negative 1 and store it back in row 2. So I'm going to just put that over here. I got... do I have room, actually? If I got room, I'd like to work vertically. Okay, I gave myself lots of room. I was nice about that. All right, So we are going to rewrite this. We're leaving the first row the same. Then we have 0, positive 1, 0, negative 4, because dividing by negative 1 is throwing it back into itself, row 2. And then 0, 0, 1, negative 2. Now, at this point, once you got this, I was a little distracted earlier thinking I wanted zeros up here early. That's not at all what I want. Once I get my powerful 3 zeros, I actually just want to get a 0 right here. And I should be able to get rid of both of these numbers now at the same time. So I'm going to take row 2, and I'm going to multiply it by a negative 1, because when I do that, it'll cancel this. And then I'm going to take row 3 right as it is, and I'm going to add it as well. So what you usually end up doing once you get this 3 zeros and then that 0 right here is that you just add these. You just need some combination of each of these two bottom rows added to the first row, stored in the first row. So it'll take just a little bit of mental math, but we can handle it, right? We are not changing that bottom row. We are so done. That tells me z equals negative 2. We are not changing the middle row. That tells me that y equals negative 4. But we're going to multiply negative 1 times 0 plus 0. That's not going to change. That's a 1. Then this here, we're adding this times negative 1 plus this plus that. But I don't care about that 0. So let's just focus on these two. Negative 1 plus 1 is 0. Then over here, again, I'm adding this one, and this one, but I don't care about that 0, right? Don't worry about that. 0 times negative 1 doesn't matter. So it's just 1 plus a negative 1 is 0. All right, and then here, this does matter. We need to be real careful. So this is a negative 1 times row 2, so that's a negative 4, plus row 3, which is a negative 2. So that is 4 minus 2, which is 2, which I hope is what we said it was earlier. It actually doesn't sound very familiar. I said it was 5 earlier? Well, oh, I haven't finished adding. Negative, what are we at? Negative 1 times a negative 4 plus a negative 2. All right, I don't want that. That's just wrong. I forgot to add the 3. So that's 4 minus 2 plus 3. That's 5. That's what we had last time. So, moral of the story is, when you get the 3 zeros, maybe go ahead and solve it. And if you want to do this for the style points, and it is cool, man. I mean, look at that. That's saying 1x plus 0y plus 0z equals 5, 0x plus 1y plus 0z equals negative 4, and 1z equals negative 2. But, once you get those 3 zeros, y'all, you are done. Now, I want to go ahead and point something out. I mean, some of y'all might think these matrices are kind of tedious. We just solved a 3 by 3 matrix in 1, 2, 3, 4, 5 steps, and that was pretty fast. I'm going to argue, actually, that especially larger matrices, 3 by 3 or 4 by 4, there is no faster way to do it, even by hand, than using an augmented matrix. That's just, it's lightning. And I can do it even less steps than I'm showing because I can combine even more. I do want to show you a little bit of the combining steps here, but it's that organizational strategy that allows us to organize our work, to combine steps and things like that, that really makes things quick. If you see some linear algebra professors or people on YouTube doing linear algebra, you can see people solving matrices lightning fast. I mean, it's crazy how good people get at it when they do it a lot. But that's neither here nor there. Anyway, I want you to do practice 5.1, make it an augmented matrix, and then I want you to get that triangle of power. That's those zeros in the bottom left-hand side of the diagonal. Yes, it's a 2 by 2 system, so it's only going to be 1 0 this time, but still be thinking about it that way. All right, pause it, and then we'll get going. All right, let's see how you did. All right, well, first of all, applaud yourself if you're able to set up the matrix properly, because that's, kind of a big deal. You got to have x's in line, y's in line. Okay. And do you remember that we said we really like having a 1 in that upper left-hand corner? So if you don't have that, do some swapping and some stuff. Do everything you can to get it, all right? Without it, you have to play with fractions. And I'm trying to avoid that just because, we're learning it, right? We want to learn with simple numbers. All right, I'm going to multiply row 1 times a negative 3, and I'm going to add it to row 2 and store that in row 2. Because I'm trying to get that 0 in that triangle of power. So I'm not changing the top equation. I'm going to multiply this by a negative 3 and add it to here. Negative 3 plus 3 is 0. That becomes positive 6 plus 1 is 7. That is negative 12 plus 5 is a negative 7. And now, at this point, I'm going to divide both sides. I'm going to divide, I'm talking about algebra. I'm going to divide row 2 by 7 and store it back into row 2. So what's that do for me? That's going to get me that 1 in that bottom corner here. I got 1, negative 2, 4, 0, 1, negative 1. We could be done right now. We really could. We got the triangle power. We could be done. We know that 1y is negative 1. We could plug that in right here. X minus 2 times a negative 1 equals 4. But let's go ahead and just finish this off by getting a 0 here. So I'm going to multiply row 2 times 2 and add it to row 1 and store that in row 1. So 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus a negative 2 is 0. Negative 2 plus 4 is 2, and then I have this unchanged. So 2 comma negative 1. And we can plug it in and check. We have 2 plus 2 is 4, 6 minus 1 is 5. All right. Would you represent this following system as an augmented matrix, but do not solve? Notice you're going to have to do a little bit of maneuvering around. Okay, just wanted to go over that. All right. Pause the video. Okay, so if you manipulate this equation, we would have negative x minus y, and then we have like a plus 0z equals 8. And then we have x, we have no y, so plus z, and then I'll move the 5 over here. Then we've got 3x plus 2y minus z equals 0. So the thing is, there's just lots of zeros here. And I don't know. You could try and solve this on your own. I just don't. I wrote this problem just to practice putting it in the right form. I don't actually remember if I made it work out to be nice numbers. I have a feeling I didn't. Since I said do not solve, I probably tried to solve it myself and had a big. Oh my goodness gracious! I did not have enough room there. All right, I'm doing negative 1. This is, I think it's going to help if you put 0z, 0y. Okay, so I have a negative 1 minus 1. Then I have a 0, and then I have an 8. Then I have 1, 0, 1, and 5. Then 3, 2, negative 1, and a 0. Okay. And we're just going to leave it like that, because that was the whole setup. All right, let's do this one. Solve the following system using an augmented matrix and elementary row operations. Ooh, wow. Okay, so this one's got some manipulating as well, right? I'm just making sure I copied down the right problem. I did. Because this equation here is not right, nor is this one. So I like the x minus y plus 2z equals 8. That one was nice. Okay. X, I'm going to go ahead and write plus 0y minus z equals 4. And then I've got 2x plus y and the plus z at the end equals 4. So what kind of matrix does that give us? It gives us 1, negative 1, 2, 8. 1, 0, negative 1, 4. 2, 1, 1, and 4. Okay, so there we have it. I need to get zeros in my little triangular power here. So what I'm going to do is I'm going to, I think, multiply row 1 by a negative 1. I'm going to add it to row 2, and I will store that in row 2. Then I'm going to take a negative 2 times row 1. I'm going to add it to row 3, and I'm going to store that in row 3. So I am doing 2 steps at once again. This is pretty much the only time that you'll see me do it in this little series, but there are definitely some other places you could do it. So negative 1, we're multiplying the top row by negative 1 and adding it to the second row and storing it in the second row. Let me go ahead and write down the first row again so we know we're not changing that. So negative 1 plus 1 is 0. Negative 1 times negative 1 is 1 plus 0 is 1. Negative 2 plus a negative 1 is a negative 3. Negative 8 plus 4 is a negative 4. All right, on the bottom row, we're not ready for the bottom row. We're doing negative 2 times the top row plus the bottom row. So negative 2 plus 2 is 0. 2 plus 1 is 3. Negative 4 plus 1 is negative 3. Negative 16 plus 4 is a negative 14. Negative 12, sorry. All right, now that I got zeros here, I'm going to get rid of this 3 by multiplying negative 3 times row 2. I'm going to add it to row 3, and I'm going to store it in row 3. So 1, negative 1, 2, and 8. And I'm not changing row 2, right? All right, multiply by negative 3 and add. 0 plus 0. Negative 3 plus 3 is 0. 9 minus 3 is 6. That's 12 minus 12 is 0, right? All right, so then I can divide row 3 by 6 and store it in row 3. But I think you ought to know what that's going to be. Okay, at this point, we've basically got it because we know what z is. We can plug into this statement to get what y is. We can plug those in here to get what x is. But just for fun, let's go back and get it. I'm going to get a 0 at this negative 3 value. I'm going to multiply row 3 by 3, and I'm going to add it to row 2 and store it in row 2. So I'll leave the top equation the same. And then that'll be a 0 still. That'll be a 1 still. Multiplying this by 3 plus negative 3 is 0. 0 plus a negative 9 is negative 9. And then I've got 0, 0, 1, 0. We've actually already got the 1 here. Usually you don't, but that's nice. We already got it. Because remember, I want 1s here and here. And then the last step, I'm going to get rid of both of these numbers here. So I'm just going to take row 2 as it is. I'm going to take negative 2 times row 3. And I'll take row 1, and I'll store the result in row 1. So that's going to be 0 plus 1 is... Oh, sorry. Nothing changes there, right? 0 plus 1. All right. That's 0. We're leaving that the same. 1 plus negative 1 is 0. Okay. Multiply that by negative 2 plus 0 plus 2 is 0. And then 0 plus row 2 is itself, so negative 9 plus 8 is a negative 1. All right, and then the others stay the same. 0, 1, 0, negative 9, 0, 0, 1, 0. Just a quick word. I mentioned earlier that that's pretty much the only time I did 2 steps at once. I'm really doing 2 steps at once here as well. You don't have to. You could just take row 2 plus row 1, get yourself a 0 there, and then take row 3 plus row 1 and store it in row 1. You know, whatever works. Sometimes it gets a little bit, crazy looking, and you just do it however works for you. So we have a solution of negative 1, negative 9, and 0. That's what we're saying is the solution. We could check negative 1, negative 9, 0. So negative 1 plus 9 is 8, plus 0 is 8. Negative 1 plus is equal to 0 plus 4. What? Okay, I see my mistake. Writing on a computer is not that easy. Do you see that I had a negative 4 and all of a sudden I became a negative 9? Probably because when I drew my 4, my pin just kind of messed up on me. So that, I apologize, but that should be a negative 4. And see, now it's becoming even more definite, negative 9. So that should be a negative 4 here as well, still. So then when I added them, I should have gotten a 4 here, right? I should have gotten a 4, which is nice because I can just use the negative of the 1. So let's try that. 4, negative 4, 0. Let's see if that works. 4 plus plus 4 plus 0 is 8. 4 equals, what are we saying? 4 is equal to 0 plus 4? Yeah, 4 equals 0 plus 4. That's right. Then we got 0, 8 plus a negative 4 is 4. Okay, that totally works. All right, a little scary there. Okay. Want you to practice 5.3 now? Okay, give this one a try. All right, let's see how we did. So you probably, if we just start off right here, we have 2, 1, -1, 5. Then we've got 1, 2, 1, -5. And then we've got 1, -1, 3, 15. It would be best if we just kind of rearrange that. So I'm going to swap some rows here. 1, 2, 1, -5. And then this will be a 2, 1, -1, +5. All I'm doing is rewriting which equation's on top. It's totally legal to do. We are totally allowed to swap rows in a matrix. All right. I'm going to multiply row 1 times a -1, and I'm going to add it to row 3, and I'm going to store it in row 3. At the same time, I'm going to multiply it by a -2, add it to row 2, and store it in row 2. So row 1 will not change. 1, 2, 1, -5. Multiply this by a -2 and add it. -2 plus 2 is 0. So that's 0. -2 times 2 is -4, plus 1 is -3. -2 plus a -1 is a -3. 10 plus 5 is 15. All right, now we're doing negative row 1 and row 3 and storing in row 3. So that makes 0. -2 plus -1 is a -3. -2, sorry, -1 plus 3 is a +2. Negative times a negative is 5 plus 15 is 20. All right, now that I've got that, I'm going to take row 2 times a negative. I'm going to add it to row 3 and store it in row 3. So this is 1, 2, 1, -5. 0, -3, -3, 15. 0, negative times a negative is +3. 3 plus a -3 is 0. +3 plus 2 is 5. -15 plus 20 is 5. So now I need to divide row 3 by 5 and store it back into itself. So that gives me 1, 2, 1, -5. 0, -3, -3, 15. 0, 0, 1, 1. Okay, I'm going to go ahead and get a 0 here by saying 3 times row 3 plus row 2 and storing it into row 2. So that's 1, 2, 1, -5. 0, -3, 0, 18. And we still have 0, 0, 1, 1. I will divide row 2 by a -3 and store it back into itself. So I have 1, 2, 1, -5, 0, 1, 0, -6, and then 0, 0, 1, 1. Now at this point, I'm going to get rid of the 2 and the 1 from the top row by taking row 2 times a -2 plus row 3 times a -1 and adding it to row 1 and storing it in row 1. So that will be just a 1. That's going to give me that 0 there. That's going to give me my 0 there. And the only one that's going to be at all, we set it up to do that. So the only one that's going to be at all difficult is calculating this final number. So we want to be real careful there. So I might even do a little scratch word. So a -2 times a -6. -2 times a -6 plus a -1 plus a -5. What does that give me? 12 minus 1 plus 5 is 16. Okay. So then 0, 1, 0, -6, and 0, 0, 1, 1. So apparently it's 16, -6, and 1. Hopefully I didn't mess up this time. Let's find out. 16, -6, and 1. So 32 minus 6. Well, okay, that's not looking good for the Mudville 9 right off the bat. What did I do wrong here? Let me double check this. 12, 11, yeah. Oh, wait a minute. Is that a negative 5? Arg. Okay. Why is it that I can't do that last step? Notice how important it is to always check, boys and girls. Always important to check. So 12 minus 1 is 11. Minus 5 is 6. So 6 minus 6, 1, 6 negative 6, 1. Let's try that. 12 minus 6 is 6. Minus 1 is 5. That works. Let's see here. 6, negative 6 plus 1 is negative 5. 6 minus 6 is 0. Right? Well, hold on a second. 6, oh, minus a negative 6. I'm sorry. 12 plus 3 is 15. Okay. Good to see. All right. Let's just summarize what all we've learned so far. So a matrix with zeros forming the lower left-hand corner, that triangle of power I talked about, from the diagonal down and left, is in what we call echelon form. So echelon means like to be put in order, basically. That's basically what it means. I mean, usually what they talk about is troops, like an advancing set of soldiers. They're in what we call an echelon form. All the rows are lined up. So echelon form just means you've got everything lined up, and it's powerful. So this is kind of a military kind of thing. A matrix in row echelon form with each row having at most one non-zero entity. All right, meaning that typically it's 1 0 0 0 1 0 0 0 1, but you could have some other times where something cancels out and you have like all zeros. But basically at most one. I'm not really saying that right. Having at most one non-zero entry. I mean that in the far three. I'm only talking about the 3 columns, not the constants on the right. So basically what I'm talking about is this. When you get it like that, what does that mean? Well, that means that we are in what's called reduced row echelon form. And you really want to know these vocabulary words. These are just so important in math. Reduced row echelon form. We really want to know them. Okay, consider the following system of equations. This is this augmented matrix. If I did it right, negative 1, negative 3, 1, 4, negative 1, 5, 3, 2, 0, 2, 7, negative 3. So we would say this is the augmented matrix that represents this system. So this augmented matrix represents the system. This is that same matrix, but it's been put in a row echelon form. Row echelon form. Yeah, I just said echelon form earlier, but you might be asking, what do you mean by row echelon form? Well, there's also column echelon form. We won't be using column echelon form. It's used for something that's not in the scope of this class, but it does exist. Column echelon versus row echelon. And then the row echelon has got the zeros like that. You can imagine columns, something like that, but in a different direction. All right, but this matrix, here we go, just like that. This matrix is in reduced row echelon form. And this is the 3 by 3 identity matrix. Technically it's the 3 by 3 identity matrix of multiplication, but that's the key, the identity matrix. Boom. That means we got it. The solution to the system of equations, by the way, since we did all that work, let's say it was 34, 9, and negative 3. Okay, we're going to close a little bit of history. The technique of using elementary row operations to put a matrix in row echelon form is often called Gaussian elimination. It's named after the famous German physicist and mathematician Carl Friedrich Gauss. Carl Friedrich Gauss is like early 19th century, whereas like real matrix theory takes off kind of like mid 19th century. So kind of a little bit of a time discontinuity there. So I'm not sure that Gauss was actually using a matrix so much, or he probably was, but not calling it a matrix. But the process of elimination, you'll hear it called Gaussian elimination. Now, once we talk about changing row echelon into reduced row echelon form, you'll hear people throw around the words Gauss-Jordan elimination, and that's just throwing in another mathematician named Wilhelm Jordan. Now, of course, like most things in mathematics that we have named after someone, it's usually named after someone who did not do it first. They just did it the loudest. See, Gauss was far from the first in, and even in Western mathematics, to use this technique. Now, you have to understand there's a whole nother mathematics coming out of China and, definitely India subcontinent, and then of course the continents of North and South America, and they're discovering lots of algebra on their own, and at different times. But the most of our story comes from Western mathematics, and I don't mean to belittle anyone else, but that's just a lot where our tradition comes from. So anyway, he was not the first in Western mathematics to do it. In fact, the steps were a refinement of the steps described by Sir Isaac Newton in his physics books Principia de Mathematica, which also invented calculus. So he needed these techniques to solve those problems. So really, that's pretty much where we think Gauss gets his ideas from, because that book is, one of the most widely read works in science and math history. But, that being said, we can't start running around calling Newtonian elimination, because evidence of a similar technique can be found much earlier in Egypt and China. And the fact that it's in Egypt, now Egypt is definitely part of our Western mathematics tradition because of the Greek mathematicians that were held there. By the way, the word echelon we talked about earlier, it simply means arranged in ranks or in file. Perhaps you heard the phrase upper echelons of society. That's, kind of similar. The solution form of the matrices are called row echelon form because we're making operations on the rows. There is something called column echelon form. I mentioned that earlier, but we will not be using that here. And just so you know, we are not just doing this to solve systems. Row echelon, putting a matrix in row echelon form solves an umpteen billion different kinds of application problems with matrices. They're just well beyond the scope of this class, and we can touch on some things here and there. But I wanted to connect matrices to something that you're familiar with, which are systems of equations. But they're so important. There's an entire class devoted to them in both undergraduate and graduate school for mathematics. So anyway, I hope you enjoyed that lesson, and I will see you in the next one.